folks, welcome to the special New Year's edition of Just Enough Math, which is the same as every other edition. My name is Ahmed, and this is...
I'm Justin.
Okay. I'm a full-stack developer here at Proven, and Justin is...
I teach math over at Lodestar College.
Okay, cool. So we're here to present math topics, just enough math to help you with software development tasks, be it testing, development, times possibly even project planning. So all of our talks are available as Colab notebooks in Python, which are basically cloud-hosted Jupyter notebooks. We put the link in our LinkedIn group, Just Enough Math. Welcome to join. If you have any trouble accessing it or you're not on LinkedIn, let me know. Make sure you can access it so you can run all this code, go through the presentation, edit it, and basically play it off for yourself to get a better feel for it. Okay? We're not necessarily experts in the specific topics we present. I mean, obviously we know our stuff, and we'll approve you. And there we put in all of our links and occasionally other announcements for future sessions. Thank you. Okay? And you can scroll that again. Cool. So yes, we're not necessarily experts in the specific areas we present. I mean, obviously, I've been developing for more years than I probably remember. Justin knows his stuff as far as math goes, but we sometimes delve into some areas that maybe a bit new to us, and even get a little bit more technical in some of what we present.
Yeah.
And see disclaimers, views don't necessarily represent those of Proven or respective employers.
Sure.
And
I don't represent Lodestar College.
right. And all the code here is written just with simplicity and understanding to be as obvious to everybody as possible. Okay? Okay, so let's scroll down a bit. Stop me if you have any questions, okay? So let's go down to where, let's go, okay, there we go. Yeah, tuples. Let's go to tuples.
So what's the topic today?
The topic is
Not sets.
combinatorics.
Combinatorics. So what is combinatorics?
Anyone care to venture a guess?
Thermodynamics.
Thermodynamics? Okay.
I didn't expect that answer.
Me neither. How so?
Thermodynamics is just the sum of all the possible states.
Oh, okay.
Every single combination of religion.
We'll talk about that a little bit in the web pages. How many different states can a web
Yeah,
page be?
the observed state of thermodynamics, like temperature, everything.
Yeah.
It's just basically the most probable state from every single possible. Like 3. But the 6 is the most probable state when you roll 2 dice.
6 is the most probable state we roll 2 dice.
If you roll 2 dice, so 6 will be the observed. Is what you observe as temperature.
Yeah, I mean, okay. So combinatorics as a field is sort of nebulous. It's not exactly a well-defined field. It sort of encompasses a lot of different things. I personally think of it as ways to count. And typically this is not counting like 1, 2, 3, 4, 5. It's using formulas and various techniques and schema to determine the number of configurations of objects, or and this is where I think what you're talking about, Kai, comes in. It's you have a system that could be in any number of configurations, right? Some number of configurations depending on how its elements are arranged, right? So that's a combinatoric problem for sure. Counting the number of configurations that a system can be in is 100% a combinatoric problem, right? And this, of course, can be useful in information, right? Because you want to know what can happen in a given system. Right. So and if you have to check every possibility, well, you'd like to know how many possibilities that is that you have to check. And then when you get into what you're talking about, Kai, the most likely configurations, that's sort of an extension of what we're talking about. It's that brings in probability theory, right? So you're talking about what the most likely states are. Of course, if you want to focus your effort on being able to manage those most likely states, then that might be the reasonable thing to do. So broadly speaking, combinatorics is just it's using formulas and different methods to count, the number of configurations of certain types that a system could be. That's as fair definition as I can come up with. So, you want to add anything to that?
Yeah, be seriously.
It's an application of combinatorics though, right? So,
I was trying to be funny, I'm sorry if I.
Your sense of humor is almost as bad as mine. Okay.
Wow. I need a tell. But anyway, we got down the right. I think we got down the right road, despite that.
Just
Okay.
go up.
So
Up.
up.
We're talking about tuples. Right?
Oh shoot! Right, I forgot. That's at the beginning. Right? Okay.
Tuples.
That was the last minute change. All right. So I'm gonna take over. Talk about preliminary stuff.
Yeah. So preliminaries to combinatorics. A lot of what we're going to talk about, most of it is going to be grounded in sets and set theory and things like states. So I want to talk a little bit about that. So first you have tuples. I've heard some people call them tuples, but I refuse. They're tuples. And a tuple is just, don't say anything, it's just a collection of data that has an order. In this case, this tuple happens to be a two-tuple or an ordered pair because they're two items. And again, it's pretty obvious, right? 1, 2 is basically an entity having a value 1 and 2, and the order matters, so 1, 2 is not the same as 2, 1. And we're going to get into details with like tuples and more than two tuples in a bit. But keep that in mind, a tuple is, because we're going to contrast it with sets.
Yep.
Okay?
So just as a side note, I'll never go to war with you because you will die on every hill. Every hill, like just the first hill you see.
Yeah, I've never found a hill I didn't want to die on, but it's true. Yeah, I think
I won't say tuple.
Yeah, I refuse to say tuple. I'm going to die on that hill. Okay, so sets. So the reason why I emphasize the idea of ordering in tuples, not tuples, is because we contrast them with sets. And the set is a collection of items where the order doesn't matter and where there are no duplicates. Or if there are duplicates, they don't matter. Okay? And there's some terms that go with sets. The size of the set is cardinality. We call it cardinality. That's basically the size of the set, the number, which is the number of elements in the set. So
We use little bars to indicate the cardinality.
yep. If this is a set, those little vertical bars indicate its cardinality. So if you have this set here that consists of 5, pi, 7, and 1/2, and it says S, then the cardinality of S is 4. Straightforward? Okay? And again, we're going to build a lot of things on this foundation, okay? So, set membership. Okay? Another thing to keep in mind when we talk about sets, there's several operations that are supported on sets. The only ones that are really going to be relevant for today's talk, one of which is set membership. And this just simply lets you know if an element is in a set, okay? And an element is just basically what we call something that could be in a set. So if you have a set 1, 2, 3, and notice in Python, we just put the sets in curly braces. It's a whole thing with dictionaries, but it effectively works out the sets. 1, 2, 3 is a set. We have the number 2, and if we use the keyword in, it'll return true if 2 is a member of the set, which we can see it is. Converted, yeah.
So we can have 4.
Yeah. And then if you ask if 4 is a member of the set, then the answer is false, right? Very simple. An element is a member of a set if it exists in that set. Okay? So far, so good? Okay. Now, since sets don't care about order or duplication, the only thing that matters when comparing two sets is that they have the same elements. So for example, set A is 1, 2, 3, 5, and 4. Set B is 1, 4, 3, 2, 1, 5. Set B has more elements than A, well, it has duplication, and the elements are in a different order, but it doesn't matter. A is equal to B because order and duplication in sets don't matter. All that matters is that every element of B is in A and vice versa. Okay? Okay, cool. Now you want to jump in, and we'll see why this matters because we're gonna talk about the Cartesian product, which is important for generating these states and configurations.
Yep.
Do you wanna make this smaller? Because I think this is getting cut off.
What's a question, Brian?
Yeah, so the thing is like here, that's like the literal, right? So you have one repeated, but in reality, right, when you actually get the set,
Yeah.
you don't have it two
Exactly.
ones, right?
Right.
So
Exactly.
the cardinality would still be the same.
Absolutely.
Yeah.
In fact, if you want, can you put in the line print B after line 4? Or even B, or just B. Let's put B and then run it. Yeah. And so here we ask Python, and notice it says 1, 2, 3, and 4. 1, 2, 3, 4,
Yeah.
5 is B. You're right.
So
So,
internally, it already understands that this set that's called B is in fact just 1, 2, 3, 4, 5.
yeah. Exactly. So you're absolutely right. Yeah.
So the mathematical definition of a set does not allow
Yeah.
duplicates.
Yeah.
Right. Right. Yeah. And if you were to get the cardinality of B, like LE and B, you'll of course get 5 because you're 5 balance. Absolutely.
But the way I explain to my students is that it's okay to write B like this. You can write it.
Yes.
It's not wrong to write it with duplicates. It's just that as a set, we understand that it doesn't contain 2 ones. It contains only 1 1. So it's just any duplicate you see is just like redundant information.
So the assignment actually gets rid of the duplicate.
The assignment?
Yeah.
What assignment?
So you say B equals.
Oh, we're comparing them, right? So we're comparing A and B. We're not assigning them.
No, the assignment.
Oh, I see what you're saying. I see. You mean line 3.
Equals, yeah.
Okay.
it does, yeah.
Okay. Yeah, yeah.
Yeah.
And if you were to even print it, like, could you replace line 5 and just with curly braces, like 1, 1, 2, and then hit play? Right. So even before assignment, the moment you put it in this representation, it's going to go ahead and just eliminate it. So pretty much, it's going to automatically use a canonical form of that. And I think internally they might be represented as dictionaries, and so being keys, that would be why, because it's the same notation for dictionaries in Python. Yes.
And this is just Python's way of doing it.
So mathematically you'll use braces and this notation, but right, the Python has the support for sets. Other languages would either not have, other languages may use different ways, or you may require a library in order to provide that support. Most languages I know don't necessarily have native support for sets. You can do things with like hash tables and dictionaries, but it's not quite as convenient. But there's probably going to be a library for it in just about any language you're thinking. Yeah. But this is Python's way because it represents dictionaries as braces, so it has a very nice affinity with set notation that you want to sort of get in other languages. Good question. Yeah. So your language may vary, but there'll be some support. Your syntax may just differ. And you made a package. Cool.
Is it actually a data type?
I believe this is a dictionary, because in dictionaries in Python you put in braces, and since dictionaries have keys and values and you're leaving off the values, I believe it's just taking the keys, and yeah.
It also has the keyword set.
Yeah, there's definitely a keyword set, yeah. And in fact, if you like, put in an empty set, like if you take out all those values, it'll just return, okay, this one return that. I guess you could do like, there's some operations where you get back an empty set, and you'll actually just see set, and then empty parentheses. So in our cases where it shows that's what it has. And it has the keyword set. You can definitely replace that with like a key with set parentheses values, and it'll do that too. Yeah. That's absolutely Python, yeah. Good point.
All right, so talking about Cartesian product now. Cartesian product is a set of tuples, and it's formed in a pretty straightforward way. Incidentally, Cartesian product also goes by a couple different names. Some people have called it just a set product, or even a cross product, right? It's of course not to be confused with the cross product from calculus, which is a vector operation, so it's a set operation, all right? So it's a way of starting off with just 2 sets, right? Forming a set of tuples using the 2 sets, right? So if you can read this set builder notation up here. This is the set that's formed from sets A and B by taking their cross product. The cross product being denoted by a little elementary school multiplication symbol there. Okay. So what you do is you form ordered pairs or two tuples, right? By taking the first element of the ordered pair from the first set, right? Set A, and then the second element from set B. Okay. So again, pretty straightforward. But again, it is a set of tuples formed from two sets, and the order matters. So if you take the Cartesian product of two sets in the opposite order, that is more than likely going to change up the set that you get as a result. Unless, of course, they happen to be equal. So, but as long as the two sets are not equal, then their Cartesian products are not equal. They are, however, very similar to each other, as you can see from this example, right? So what's the similarity? So if I take this set that contains 1 and 2 and do Cartesian product with the set that just contains 3, this is what I get, right? On the other hand, if I switch the order, this is what I get. So what's the difference between these two sets? Just basically, they're mirror images of each other, right? So if you switch the order, you just switch the coordinates of the results, right? So, but in general, because order matters, with tuples, then we call those sets different, right? We say they're different. So this whole mess of symbols here, is just just the generalization to more than two sets, right? If I have a whole collection of sets, set 1, set 2, up to set k, I can form a k tuple, right, from using elements of those sets in that order, and form a set of those k tuples, and that's your Cartesian product of k sets, right? Okay, so just as a quick example, if I have sets A, B, and C defined this way, then I take their Cartesian product of these 3 sets in that order, A, B, and C. I get this collection of 3 tuples. Right? You notice that, of course, they all have the first coordinate in common, the 2, because why? Because there's only one element in set A, that's the number 2, right? So the element in the first position of every tuple has to be from set A. There's only one element in set A, it's 2, so that's why the first element in every tuple is a 2, and you'll see that every element in the second, every second element in every tuple is either 1 or 4, and so on. Right? So
we'll pause. Any questions? And he said 3 tuples, and that means like an ordered triple, not that the set has 3 tuples.
Yeah.
It has 8.
3 tuples.
Or 6 tuples. Yeah.
It has 8 3 tuples.
Or 6, right? 6 tuples.
Oh, yeah, 6.
Or 6, yeah. I can't count.
You cannot. But counting, you cannot count and still do combinatorics.
Okay, we'll do it.
All right, so moving on. So now we're going to talk about the cardinality of a Cartesian product. It's sort of, this is probably for many a straightforward, thing, right? Okay. This is how you calculate the cardinality of this Cartesian product. So if I have a Cartesian product, from sets 1 through k. But I know the Cartesian products of all those components, then I just multiply all those numbers together, and that gives me the cardinality of the product, okay? So that maybe is, unsurprising. If you look back up here, you can see just a quick example of that, right? So what's the cardinality of set A? 1, right? And then set B is 2, set C is 3, 1 times 2 times 3 is how much? 6. Notice there are 6 3 tuples, right? Okay. So, to get into a more interesting example, we have this extended little word problem here. So, a mathematician has to get dressed in the morning. There are 3 tops, 4 bottoms, and 2 pairs of shoes to choose from. In how many ways can this abomination play out? So what do you think? So So in terms of sets, right, if we want to phrase this in terms of sets, what do? We say, okay, I make a set out of my tops, right? We have, we chose these interesting tops here: butterfly collar, turtleneck, and dashiki. Your bell bottoms, you got your bottoms as bell bottoms, Bermuda shorts, corduroys, and parachute pants. So I don't know. Mathematicians are hipsters. Is that the?
Well, this kid dress.
Although parachute pants are not exactly hipster, but I think pretty well. Neither Bermuda shorts, but I think almost everything else is. But anyways, so okay. Point is that these sets have cardinalities, which you can easily see, right? What is this cardinality of the tops? 3, right? What's the cardinality of the bottoms? 4. What's the cardinality of the shoes? 2. So how many different outfits are there? 4 times 3 times 2, which is 24, right? So, and that just comes straight from that principle, right? So here's just a quick list of them all, right? So we've got your, every element is a 3-tuple, right? Representing what? An outfit, right? So okay, so which just choosing a random outfit here. What do we have? A dashiki, parachute pants, and hemp sandals. You got your turtleneck, parachute pants. Why do I keep choosing parachute pants? Parachute pants and hemp sandals. So all these different things. Got a butterfly collar, bell bottoms, and Crocs. One of the I put my phone on Do Not Disturb. I did. Yes, it says Do Not Disturb on.
Just turn off your phone.
Can you scroll
You
back?
always do not disturb, huh?
Can you scroll back up to the code?
Sure, can you scroll up to the codes?
Yeah.
So just so you know, there's actually a built-in function that'll do a Cartesian product. I think it's called product, and it's part of a package. All that cart_prod does is just kind of makes it a little cleaner to use, because whenever you call a Cartesian product in that function that's built in, it gives you back like a generator, and so you have to just wrap it in a list to basically get its elements out there. But that's all the stuff. In fact, can you go all the way up to the preliminaries just to? Yeah. So in fact, yeah, because it's all built in. It just makes it a little less irritating to use, just because otherwise you wrap it in a list and get stuff back. I think generators help us delete stuff. Go to set theoretic functions and expand that, please. Yeah, or show code. So you see right here, all that cart_prod does is it calls the product function, and that's an import. I think it comes from Python's itertools package, and it just returns what they call a generator function. If you notice, I wrap it in set. Okay, we're step down, and that just basically forces it to spit out all the elements. Yeah, but otherwise, all the stuff's built in from the itertools package. In those Cartesian products, permutations, combinations, all the stuff's going to talk about is already in a package for you. Yeah. But Python will do that a lot. It'll put stuff in a generator so that when you spin it back out, it's like, oh, it's a generator. Set or list, and it forces the generator to actually really just give you all of its elements. And yeah, that's why I wrote these functions, just to kind of, so I don't have to put in list and set every time, which got to be a bit irritating. Cool.
All right. So
Yeah.
any other questions?
Cool. I guess we
So Ahmed, I believe you have prepared some talk about testing states.
Yeah, sure. Yeah, so there's an application to that. There's actually something that Nick also mentioned, and it involves testing. And this is actually something that I've also done, and literally last month I had to do it again. So probably 2 or 3 days after our talk, I had to do this again. So what happens is this whole notion of a state, okay, can represent the state of an application, like the state of like your web page, all the inputs, right? So for example, you have a web page, and I just throw in a dummy form here. And there's a lot of different inputs a customer can choose, right? For example, in this case, the customer may choose a delivery method, right, which is a drop-down box, that, or a customer type or a subscription. They may have input boxes where you put in different values, right? They may have checkboxes and so on. And so each one of these inputs is, you can think of them as a set with possible values, right? So the delivery method is the set consistent of home and whatever other values are their home, and it gets shipped to store in Dropbox. So customer goes through and they can pick home with premium or home with budget or to store with loyalty and so on, right? They can pick a bunch of different values there. Once they pick all of their values, all of their inputs together forms one state, which is basically one element of the Cartesian product of all of these, right? So if you take the Cartesian product of each of these inputs, you get all of the possible states that page can be in from that inputs, right? And then from there,
2, 5,
yeah, and then 2, right? And so now you're like, okay, I know this page can be in all these states. I have all these states. Now I want to test them. And when you write automated tests, you could write automated tests to exhaustively go through all of them, or even go through some of them. But being able to generate it makes life a little bit easier. Now we could loop over every state and put a nested loop in there. But that gets to be a bit of a pain in the neck because 5, 6, 7, 8 forms, do you really want a loop nested 5, 6, 7, 8 deep? So it's cleaner to use a Cartesian product, right? So if you scroll down a little bit, so you can see here, these are all basically the values that particular page, each of the inputs can be in. And when I get the Cartesian product of all of them, I now have all of the states. Any input the customer chooses, any combination, is going to be represented in one of these states. And in this case, that gives me 20 of them. At this point then, I could just iterate and loop over all of them and have an automated test to confirm that this page operates properly in all the inputs. Questions so far? And I've actually used this both to test functions, but also to actually write code to generate tests scaffolded for all the different states and even a testing spreadsheet to basically go through that. And that can even be done for functions if your functions have like enumerated types. Can you scroll down a little bit? Now, the other benefit of being able to generate that is that you also could easily randomly sample some of those states. Let's say you have a large number of different input fields, or they have a large number of values. You could end up with like 500, 1,000, 2,000 possible states per page. Now, you could write code to automatically test them, but that's going to take a while to run, especially if you're doing an end-to-end test. So what you could do is, now that you have it as a Cartesian product, it makes life simpler because you can say, okay, I got this Cartesian product. You know what? I can't test all these 5,000 states. Let me just get a random sample of them. Right? Pick a certain number randomly and just test those. And then every time I run my tests, it's going to pick a different random sample. Like if you hit play again on this guy, or run again. So every time it's picking a different random sample. And so this makes it easy to also have all of your state inputs grab a random sample, which again is going to be more of a pain in the neck to do inside a nested loop and decide whether or not to choose that state that you get to. And then every time you at least run your test, it's going to be faster. You're going to pick a random sample, but every time it's going to be a different random sample, which gives you a good idea of increasing test coverage by using your Cartesian product. Does that make sense? Sure.
Where did you, so you're printing out all these, oh, you're using this, print enumerations?
Yeah, and all this does is just prints all of the states and also gives me the length.
First, up here, you took the Cartesian product of your, 3 sets.
Right.
Type, customer type, product type.
Each of which represents like an input box or drop down.
Right. So now you have, now states is a thing that you can iterate over?
Absolutely, yeah.
Right.
Yeah, you can loop over it. You can do
So,
that.
and states is this, right?
Yes.
So this set of 3 tuples here.
Exactly.
So you can just, instead of, you said this would be like a nested, a nested loop of 3 loops, right?
Yeah.
Without any of this, but once you introduce this infrastructure, you just have one loop. And then you could see how this could, like, so there are only three things here, but if you had like 100 things, then you don't want to have a nested loop over 100 things, right? It doesn't make any sense. So it's just, I'm sure there are other ways to get around this, but this is one way.
Yeah. And then it gives you the ability to easily randomly sample and only test a portion of your page at a time rather than going through everything. Because some of these tests can take a long time to run. So that's one case where you're doing that. And if you have like inputs that say use input boxes, like say numbers or whatever, you could also have your sets defined by different behaviors on those numbers, right? Like if your income's above a certain amount, maybe there's different behaviors. Then you just basically have a set for, hey, I know that this value is going to be above or below this income. So you can also have ways of sort of impacting even input boxes into this set of states. Okay, questions? Cool. I guess now I want to talk about permutations and combinations.
All right. So, sort of the next step in learning, basic combinatorics typically is to learn about these two things, these two objects, the permutations and combinations, which are similar things, but they have important difference. So, what a permutation is sort of like an arrangement or a rearrangement of objects, right? So you might be familiar with this, if you talk about a permutation of something, you think of it as like just a reordering of those things, right? If I take a set contains the numbers 1, 2, and 3, then a permutation of that is 2, 1, 3, or so those same numbers but in a different order. Right, so that is the general idea. The only extension to that here is that you might have some larger set of objects that you're choosing from. Okay, so you maybe choose some subset of those, right? And that subset can be ordered in a variety of different ways, and we call each of those a permutation of that subset of that size taken from the larger set. Okay, so. Let's kind of go through these bullet points. Take our time a little bit with this. Okay. So permutations and combinations actually, first of all, have some things in common. They do the same. They do the same thing in the sense that they count the number of ways to choose a sample of objects from a pool of objects. Right, so you've got some bigger pool of objects, and you're choosing a sample, which is possibly the entire pool, or some smaller number of objects. Right, both permutations and combinations do that. All right. The choosing, and this is again what they have in common. The choosing from the larger pool is assumed to be, quote, this is jargon, without replacement. And what that means is that you're taking a sample from the pool, right? But once one of the objects is taken to be in the sample that you're taking, right? Then it is not replaced back into the pool to be chosen again. Okay. So I always think of okay, I've got like a bowl of marbles or something like that, and I take them, maybe I take them out one by one. Maybe I take a handful out or whatever. But the point is that what I'm not doing is I'm not choosing a marble and then putting it back so that it could theoretically be chosen again in the same sample, right? That's not happening, all right? So examples of things that where this is not the case is like if you construct, like a phone number or something like that, right? You can have repeating digits in the phone number, right? If you think of like constructing the phone number as sampling digits, right? I could have my first two numbers could be 7, 7, right? Right. So the 7, once I chose the 7 for the first number, it went back into the pool for me to choose again, right? But if I insist that digits cannot be repeated, then that is without replacement, right? So there's a contrast between with replacement and without replacement. Both permutations and combinations are without replacement, all right? Okay, so where do they really differ? They differ in one important sense. That's that with permutations, as I mentioned earlier, we're really talking about an ordering. Okay, we're talking about items arranged in a certain order. All right. So a set of 1, 2, 3. Right, is considered, really, I shouldn't say set, I should say a tuple, right? Because a tuple has ordering to it, right? So a tuple 1, 2, 3 is considered different from a tuple 3, 2, 1, right? Or 2, 1, 3, etc., etc. That's the case with permutations, but with combinations, no, they're considered the same. Okay, so typical examples would be like, okay, I'm going to choose a PIN number, or phone number, or something like that. That's where order matters, right? Like you don't have the same phone number or PIN number with somebody just because you have the same digits. They also have to be in the same order, right? So that's an example of a permutation. Whereas a combination would be something like if I just choose a sample of people from this room, right? There's like once I choose, you know, Brian and Nick and Kai, right? That it doesn't matter if I chose Nick, Kai, and Brian or whatever, right? The ordering there just doesn't matter. That's what you call a combination, okay?
So they should really be called permutation locks, not combination.
I don't know what you mean by locks.
Oh, yeah, locks, like you know those things that you put around
Oh.
stuff so people
Oh.
steal it?
You mean locks? What do you mean? What are these locks of which you speak? So
I mean, I like it, I agree. It should be
yeah. The order matters with combination locks. That's it.
Marketing, I'm gonna try to patent that, yeah. Okay. Patented permutation locks.
A combination lock is not a combination lock.
Exactly.
It's a permutation.
It's a permutation lock. Yeah. Yeah. Ahmed, go down the hill. Forward march. Okay.
Good observation. I like it, that's actually a good observation.
That needs to go into the blooper reel. Okay. What do you mean by locks? Okay. All right.
Dreadlocks.
What are these locks? I don't know. Okay. So, all right. So just as an example here, just a quick example. Say you're taking permutations of this set 1, 2, 3, right? But here again, we're not taking the full set. We're here in this example. We're choosing just 2 of those items at a time, right? So 1, 2 is a permutation of that has 2 elements in it from that set, right? 1, 2, 1, 3. In fact, these are all of them, right? 1, 2, 1, 3, 2, 1, 2, 3, 3, 1, 3, 2. So these are all different permutations taken from this set that have size 2 or length 2, however you want to call it, right? They have 2 bits, right? I could take permutations of this set where I take 3 items, right? And that would be like 1, 2, 3, 3, 2, 1, 2, 1, 3, right? I guess that's it, right? So on the other hand, combinations of size 2 are just these. Right, 1, 2, 1, 3, and 2, 3. Right? All right. So notice there's the subtlety in the notation. For permutations, I use tuples because order matters. For combinations, I use sets because sets are by their construction, order doesn't matter.
You said tuples, tuple. But anyway, yeah, so the tuple 1, 2 is not the same as the set 1, 2. Right? So the tuple 1, 2 is not the same as the set 1, 2.
That's right. They're not the same. Because with the tuple, or the tuple or the tuple, the order matters, and with the set, the order doesn't matter. Okay, so I think that's weird.
Questions?
All right. Stop me. All right, so we have to get into factorials, and we have to get into the weeds a little bit here if we're going to talk about this. But everybody remember what a factorial is? Factorial. Who wants a review of factorials? All right. Well, you're going to get a review of factorials. Okay, so factorial, to take a factorial, you have to start with an integer. Think positive integer, but as you see, 0 is also going to be defined. But what you do to compute a factorial is you start with the integer, right, and then you just list up all the positive integers that are smaller than it, and then you multiply them all together. That's right. So for example, 5 factorial, which is, by the way, factorial is denoted by this little exclamation mark. Okay, 5 factorial is just the number 5 itself times every integer that's smaller than it, right? It comes out to 120. Okay. And now finally, by definition, you need 0 factorial to be equal to 1 and not 0. It's a mystery of the universe, just forget about it. Okay. But you need it to be that way. Okay? All right. We might even see an example where it is that way.
Yeah, we reduces
Where you need that, right? Yeah. So okay. So now here we get to the actual math of permutations. Okay. So again, n is the size of the pool of objects. So it's a big pool of objects that we're going to choose from. We're going to choose sample of R objects from that bigger pool of n objects. All right, so this is the notation that is commonly used. Whoa. Oops. Messing around with this thing. So this is the notation that's commonly used. Subscript and P for permutation, subscript R. So that's choosing R objects from a pool of N objects and we're counting the permutations. So this is the counting aspect of it. We have a certain pool of objects, and we're going to sample, some objects, some number R objects from that pool of N objects. We want to know how many different ways that sample can play out, right? How many different permutations can occur. So this denotes that number, right? I don't know how to read that actually. It doesn't have a nifty way of reading it. N permute R, maybe it's the default way of reading that. I don't know. So it does have a formula, right? Here's the formula. So I tell my students this is the dumbest formula ever. I'll tell you why. Because you never need it for anything. All right. This thing just comes out of what you call the multiplication principle, which is very much akin to the multiplication sort of multiplication principle that we introduced for multiplying cardinalities of sets and so on. All right. But okay, let's go through it for just a second. To count the number of permutations, you start sort of like you're doing a factorial, right? But you don't stop at 1. Okay, you stop here at this number. Okay. So the easiest way to compute this is to multiply n times n minus 1, and then go all the way down to whatever this number is, and just stop there and multiply them all together. Right? This formula says essentially the same thing. Can you see why? So if you expand out the n factorial out to n minus r, and then you cancel everything, you're left with n minus r plus 1. Okay, at the end. So everything's just going to cancel out. Anyway, that's not important. That math right there is not important. The important bit is how this formula works. All right. And again, we're going to use this part. Right. In fact, let's do the example, and then we'll do the special case. So just to see an example of how that formula works out. Let's take a look at this. So say we have n equals 10, which means what? We have 10 objects that we're sampling from, right? But we're not sampling all 10, we're sampling 4 objects out of 10, right? So let's calculate how many ways that sample can occur. So the quickest way to do that is just calculate that number, n minus r plus 1, all right? So what's that? It's 10 minus 4, which is 6, plus 1 is 7, all right? So then you start to compute the number of ways that the number of permutations that can occur. You start with n, which in this example is 10. You just act like as if you're doing a factorial. You go down all the way down to 7. You stop there, multiply. It comes out to, 5,040. Okay. So any question on that calculation? It's okay. So one way to think about that is this way. You're constructing a sample of size 4, right? You've got 10 objects to choose from. Think, 10 of your favorite marbles or whatever, right? You're going to choose 4 of them, okay? When you start taking the sample, how many choices are there? 10, right? I have 10 marbles to choose from, okay? Sampling is without replacement, so I put it in my hand, I don't put it back, right? Now how many choices for the second marble? 9. Okay, done. Now how many choices for the third marble? 8. 7. Sample is finished because I chose 4, right? So it's 10 times 9 times 8 times 7. Okay? All right, so let's talk about, in fact, let's go backwards even more. So let's talk about this example here. How many 4-digit PIN numbers are there where we do not reuse any digits? Oh, sorry. sorry. Oh, I totally goofed that up. This was meant to be the solution to that. That was supposed to be hidden. I messed up. So this is actually the calculation that does the PID number question, that answers the PID number question. So this calculation was meant to answer this question. So why is this the calculation for this question? Because what? How many digits are there? 10, right? PIN number is 4, in this case length 4. So we're constructing a 4-digit PIN number in which we don't want to repeat any digits, right? And so yeah, so this is the calculation. It's a permutation of 4 objects taken from the set of 10 digits, right? What are the 10 digits? 0 to 9, right? So that's the calculation. Okay, this special case is interesting. If we look up here for just a sec. So say we're choosing all of the objects, right? So how does that computation go down? So I've got my 10 marbles or whatever. I got my 10 marbles and I'm gonna choose all of them, right? How many ways can that happen? Well, extending the logic from before, you have 10, 9, 8, 7, 6, all the way down to 1. So it comes out to n factorial. Now, this is maybe a technicality, but it gets to why 0 factorial is equal to 1. It's because if n is equal to r, then n minus r is what? 0. So you end up taking 0 factorial. So you need 0 factorial here to be 1. You definitely can't do 0 because you can't divide by 0. Okay. So anyway, that's one reason. All right. So just as a quick example, permutations of this set. Sorry. What is this on? This is the permutations of the set 1, 2, 3.
Yeah. So if you show the code, in fact, you show the code, right? So I'll show code. Yeah. So in this case, we just have a set 1, 2, 3.
So yeah, Ahmed, you wrote this function.
Well, again, all it does is it calls the permutations function and just basically wraps it in the set, so it pulls it out of the generator. For all intents and purposes, it's built in.
Okay.
It just saves me from extra keystrokes because
Sure.
yeah. So basically, it just generates something. So you can see here how many items you get back when you get the permutation of the set 1, 2, 3.
Yeah, and what does the formula tell us? Again, as we just talked about, it's n factorial, right? Because we're not taking a permutation of a size less than n, right? Here, n is equal to r, then 3, right? So, so we're just permuting 1, 2, 3 around. How many is that? 3 times 2 times 1. That's 6, right? 6 permutations of 1, 2, and 3. They're there. Okay. Here in this example, what's going on is we're taking the permutations of the set 1, 2, 3, 4, but we're taking permutations of size 2. Okay. So, what does the formula say? Basically, n times n minus 1, right? So what is that? So n is what? 4, and then n minus 1 is 3, so 4 times 3 is 12, right? Okay.
And then just basically list out all the permutations, you list all of them, and of course you can see what those are, and just every ordered pair that could be basically divided into this.
Yeah, any ordered pair that consists of the numbers 1, 2, 3, and 4. That's what permutation is. So I hope it looks less mysterious than it did maybe 5 minutes ago. All right, so now we get to combinations. Again, with combinations, order doesn't matter. We do have some special a special symbol for that. It's the big parentheses with n on the top, r on the bottom. This is also called a binomial coefficient, if you're familiar with that, or Pascal's triangle, like we were talking about earlier, right?
Was it last time we did that when we talked about the reach model, we used the binomial?
We used the binomial distribution, which used binomial coefficients. So yeah, combinatorics was already in there in the binomial distribution. Okay, so here's the gist of the math behind combinations. So if you do, oh, by the way, this has a nifty way of reading it, which is n choose r. That's just, I don't know, like slang. N choose r. So I might find myself saying n choose r when I say this, okay? So combinations are, first of all, related to permutations by this formula. So, and that makes sense, right? They have to be related. Does that make sense? when you look at it, so if you look at this, if we just look at this example right here, right, we see that, of course, we see that we can read the combinations here from looking at all the permutations, right? Because why? Because look at like 1 and 2, right? That's a permutation, right? It has a certain order, but as a combination, it's the same as 2, 1, right? Okay, and likewise, 1 and 4 is the same as 4, 1, and so on and so forth, right? So I can sort of group these together and then count the combinations. So how many combinations are there, right? So I got 1, 2, I don't know, 1, I don't know, I can't do it. 1, 4, 1, 2, let's see, 1, so each one has only one other partner, so it has to be, yeah, so it has to be 6, yeah, it has to be 6, okay, does that make sense? There have to be 6 combinations here, right? So, okay, what's the calculation using the formula? So n is 4, r is 2, so going down to the formula, right? Oh, what was r? R was 2, right? So if r is 2, how much is r factorial? 2, right? What is NPR? N permute r? Well, we just looked at it. It was 12, right? It was 6 divided by 2. I'm sorry. 12 divided by 2 is 6, right? So that's why you have to, so in this case, you're just dividing the number, and for that example anyway, you're just dividing the number of permutations by 2. So, and it makes sense that you have to divide by r factorial, because that's the number of permutations of like once you choose the numbers, right? So just abstractly, once I choose r things, right? That order that it came out to is equivalent to r factorial orders, right? So that's why you have to divide by r factorial. Because how many permutations of that set are there? R factorial, right? Right? Do you see what I'm saying? So, you got me? So once I choose, so like, okay, say I choose, so I've got 1, 2, 3, 4, 5. I choose, you know, 1, 2, and 3 out, right? So, okay, if I care about permutations, then okay, my order was 1, 2, 3. But how many different permutations of that sample are there? That sample is 3 things, right? So the number of permutations is 6, right? So there are exactly 6 permutations of that sample that I chose, but if I'm considering combinations, all those 6 permutations are considered the same as one combination. So that's why I'm dividing by, when I divide by r factorial, I'm dividing by the number of permutations of the sample, right? So this is the this is the formula that's often used to do these calculations. So it's n factorial divided by r factorial, n minus r factorial. Quick example, if n is equal to r, what does this come out to be?
1.
Yes. Why? Does that make sense at all? How so? How does that make sense?
There's only one way you can put it over.
Yeah. If you don't care about order, right, there's only one way to make that choice, right? If I've got n objects and I want to choose n of them, and I don't care about the order in which I choose them, then there's only one way to do that, right? I choose all of them. Done. That's it. Right? What about like n choose 0? What's that? n choose 0. So these are what you call edge cases in your software development.
Right? Software development.
Yeah, edge cases. So n choose 0, what's that? Well, it's 0 factorial over, it's n factorial, 0 factorial, which is 1, and then n factorial again, so it's again n factorial over n factorial, which is 1, right? So it's kind of a degenerate case. Looking at you, Ahmed. So, what are you actually saying there? You're saying I've got n objects, and I'm choosing 0 of them, right? It's kind of a silly thing to think about. What am I doing? I'm just like standing there not choosing anything, right? It's like all these objects, I'm just not choosing anything. So technically we say there's only one way to do that. You just stand there and do nothing, right? You don't choose anything. It's like you have, what do you call that? Analysis paralysis, where you can't make a choice. All right, I'm making too many choices. All right. All right, so, okay, combinations of a certain length, okay, I've got, six objects,
And he just calls the combinations from inner tools, and again, wraps it in a set. So that's all these functions do. It's you've used inner tools and pull them in, you've got all of it, all this functionality.
So now we get to the big, the icing on the cake. Okay, so what we're going to talk about is a way to use combinations, right, in a sort of a creative way. Right. So we're doing like kind of a creative visualization method. Okay, we're doing like a creative visualization method where we have a problem and we just visualize it in a certain way, and that allows us to state it in terms of combinations. Okay. All right. So here's the problem. We're distributing cookies to kids, right? So we have 10, how many cookies is it? 7 cookies. 7 cookies, 4 kids, all right? And these are Charles Dickens rules for distribution, so kids can get 0 cookies, that's possible, okay? So it's possible to have an allocation of 0 cookies for a kid, 1 or more kids, right? But all the cookies must be distributed, right? So there's 7 cookies that must be handed out. But with the possibility that some kids get 0. So 1 kid could get all 7, something like that. All right, the number of ways that this can happen is, in fact, 10 choose 3. But how do we know that? Okay. So this is where the creative visualization comes in. So everybody, we're going to use stars and bars. And if you don't use stars and bars, you're just not patriotic. That's all there is to it. So, all right. So you can visualize the cookies. You can use stars and bars or dots and whatever you want, whatever 2 symbols that you like. Okay. But you have to interpret them this way. One of the symbols, in this case, the star, is going to represent the cookies, right? And the other one is going to delineate between bins that the stars go into, right? And for us, the bins represent the children, the kids, right? All right. So again, the bars are placed between the stars to delineate bins. So we've got basically a string of symbols, okay? So here's a sample allocation, or an example allocation. Kid 1 gets 2, kid 2 gets 3, kid 3 gets 0, kid 4 gets 1. Okay.
It's only 6 cookies. How did the cookie?
How did that happen?
Oh, I was changing to show the example. Yeah. So just give kid 2 4 cookies.
How do I do that?
Or just click on kid 2.
Oh, I see.
Oh, that's fine. Kid, yeah, we're not going to go this one.
4.
Yeah,
4 is
four.
different.
There you
Number
go.
is different, right? So 2
There you
or
go.
4, and then 1 makes 7.
Yeah.
Okay. So okay, how is this symbolized in stars and bars? Okay, so we see the stars and bars string down here, right? So the bit again, bars delineate between the bins, right? So this is bin 1. 2 cookies go to kid 1. Okay, okay. Kid 2 gets 4 cookies. Kid 3, because we have the 2 bars adjacent to each other, gets 0, and kid 4 gets only 1 cookie. Okay. So you see, basically, the key to setting up to using this technique is setting up kind of a one-to-one correspondence between the configurations you're trying to count and these strings of symbols, right? Okay. So this is how I understood it. All right. So you need to clearly define kind of the rules of symbol generation, right, to make this technique work. And you can modify the rules to solve different problems. Okay, so we have to clearly state what are the rules for this problem. All right. So there's a total of 10 symbols, right? 10. Imagine 10 enumerated blanks, like the way I've kind of laid them out here. So I've got 10 blanks. All right. Make this observation that choosing the placements of the 3 bars determines the placements of the 7 stars, right? So once you choose the bars, all that's left is putting the stars in, right? So you can just talk about placements of bars. You don't have to talk about placements of stars, right? Does that make sense? Right? Once I put the bars in, I've got 3 bars, right? Once I place them, that's my choice, right? The stars have to go in between the bars, that's the rule, right? So I can just talk about this problem in terms of placing bars into these slots here, like that, right? Okay, so the pool of objects that you're choosing from is actually the 10 blank spaces. So in the setup of combinations, right, I'm thinking of like I have 10 marbles or 10 things that I'm choosing from, right? So if I visualize this way, in addition to, you know, the stars and bars bit, I have these sort of slots set up that I want to place the bars in, and of course the stars after that. I'm choosing from this pool of 10 slots. And how many choices am I making? 3, right? I'm choosing 3 of these 10 slots to put a bar into, right? So that's where the 10 choose 3 comes from, okay? So yeah, choosing placements of 3 bars determines the placement of the 7 stars. The pool of objects being chosen from is the 10 blank spaces. Each choice of a space represents a placement of a bar in that space. The number of choices is 3, the number of bars. Choosing is of course without replacement because you can't place the bar into 2 bars in 1 slot, right? So this gives us 10 choose 3, which comes out to 120, right? Just a quick conceptual test. 10 choose 7 is also 120, right? And that is also a valid way of doing this calculation. Any idea why?
It's symmetric.
Symmetric? The formula is symmetric, that's true.
I guess you're kind of, instead of looking from one of the bars, you're looking at like the interesting spots for the cookies.
Yeah, exactly. So you just shift the emphasis onto the stars instead, since there are 7 stars, right? So now you just choose, where you allocate the stars, and again, the bars have to go between them still, right? So the rest of the bars have to be, the remaining spaces, I should say. So yeah. So this is good. Maybe you'll leave it at that. What are we doing? What time did we start?
Started at 6:33. Yeah.
So maybe just kind of like speed through.
Yeah, I'm gonna jump straight to the middle bit of work, I think, just
Sure.
a bit of a program application.
Yeah. So this bit here is just the kind of the general treatment of the cookies and kids problem. With n is the number of cookies, k is the number of kids, and so on. So there's a formula for that. Here's another application. So if you're trying to configure a neural network, right, it works in a very similar way. So this.
Why would you want to configure a neural network? Why does it even matter?
Okay, you're confident. Skip it.
Yeah, that's kind of a key point. But why would they care?
All right. So neural network is a machine learning model, right? Where if you have these, you kind of think of a neural network as a graph, right? That has all these nodes and these connections between the nodes, right? The nodes themselves are referred to as neurons when you're talking about neural networks. It's modeled on the human brain, roughly speaking. So a neural network is a model, just like many models. It can make a prediction, right? You feed it some data, and it spits out a prediction, okay, or a classification, perhaps. So you put in some data, image data, and it can classify a digit, something like that. If you feed it, images of digits, you can classify the digits and so on. So that's what it's used for. Okay, but the thing is that these things are thought of as these graphs that containing all these neurons, and the neurons are layered. Okay, so this is the first layer, right? The neurons that start with A are the first layer. The neurons that start with B constitute the second layer, and so on. So this is a 5-layer neural network. Okay. So again, we have this idea of like, okay, we've got an allocation problem, right? How many, like if I think of each layer as a bin, right? we can talk about the number of possible configurations in terms of like, well, okay, if I have this many neurons, how can I allocate the neurons to my various layers, right? So this is a combinatorics problem.
And it matters because how you arrange your neurons can impact the accuracy of your neural network.
Yeah. So having multiple layers, maybe something that greatly increases the accuracy of your model. Okay. And just the number of neurons involved as well. So you might find yourself in a scenario where you're trying various neural network configurations or architectures, as they're called, to try to find the one with the best accuracy, right? And you may find yourself resorting to just kind of like a rote search through all these possible configurations, right? So it'd be nice to know exactly how many configurations you have to search through in order to find the best one, or one that meets your performance standards, right? So this is a combinatorics problem. How many configurations are there? Now, strictly speaking, there are infinite configurations because I can have as many layers as I want, and I can have as many neurons as I want. So I have to make this a real combinatorics problem, I have to impose some kind of constraint. So we'll just go through the first one. So the first constraint that we dealt with here in our write-up was, okay, say you have exactly n neurons that you want to use, right? So I'm going to use 50 neurons, right? And I know exactly how many layers I want as well, right? Okay, how does this work? So thinking in terms of stars and bars, we can say that the neurons are stars, okay? So if we have n stars, right, and we have L layers, right, then that means I need L minus 1 bars to delineate the bins, right? So I don't need L bars, I need L minus 1, right? So if I have a string of stars, right, and I want to make 3 bins, how many bars do I need? 2, right? So that's why L minus 1. Right, so I've got n stars, L minus 1 bars. Okay, here are the rules of the configurations, right? How do I set up a one-to-one correspondence between my stars and bars strings and neural network configurations under these constraints? Okay, well, every bar must have at least 1 star on either side of it, right? So star, bar, star configuration. Everywhere I place a bar, I can't have bars adjacent to each other anymore, like with the kids and the cookies. All right, I have to have stars around my bars. All right. So these kind of configurations are out. And that's pretty much it. All right? So as an example, we have this sequence of stars and bars represents this network architecture. All right? We've got a 3, 5, 2 configuration. In other words, 3 in the first layer, 5 in the second layer, 2 in the third layer. Right? Okay. So that's how we have a one-to-one correspondence between strings of symbols and architectures. All right. So now we have to be clear about what is the pool that we're choosing from, right? What is the pool of things that we're choosing from? Here, I think of the pool of things that we're choosing from as the spaces between the stars, if I already have my stars laid out. So I imagine my stars already laid out, right? How many different places can I choose a bar, place a bar? Between any 2 stars, right? So how many places is that? That's the number of stars minus 1, right? So hence, n minus 1 is the size of my pool, right? Again, how many places am I choosing? L minus 1, because that's the number of bars I have, right? So it's n minus 1, choose L minus 1 is the answer for that. So.
Why L minus 1?
Why L minus 1? Because, yeah, so L is the number of layers, right? And we need, you got it? So again, the number of, the layers are treated as bins, right? So if I have, like 10 stars, and I want to divide them into like 3 bins, what do I need? I need 2 bars, right? So I need exactly 1 less than the number of layers, right? Okay, so, I mean, long story short, we kind of dealt with a few more, constraints. Probably the most interesting.
But they can't be adjacent. Because you have to subtract. Yeah, so let's subtract the.
I think that's what the n-1 is for. The one on top, I think, has to do with the fact that you cannot have 0 neuron layers, right? That's why you have a minus at the top as well.
Yes, correct. You mean the n minus 1?
Yeah.
Yeah, that's right. So, okay, yeah, so okay, let's have something to look at. So yeah, I cannot have a bar here, right? Because if I took this bar and stuck it here, what I would have is sort of like 0 neurons in the first layer, which is contrary to my constraint, because my constraint was I want exactly L layers, right? So in this case, I'm talking about I want exactly 3 layers, right? If I have 2 bars, then that's because I want 3 layers, right? So if I'm insisting here that it has to be exactly 3 layers, right? If that's the case, I must have a bar between 2 stars, right? I cannot have a bar over here on the end or on that end, and I can't have 2 bars next to each other, because what that means, you're basically deleting a layer if you do that, right? Does this make sense?
Yeah.
Because you were talking about like at most L layers, then you could do that. That's not what we're talking about.
That's right. So we also handled all the cases. Like if you want to deal with at most N neurons, at most L layers, and stuff like that. So that's all dealt with in the examples that follow. Okay. So yeah. So we kind of touch on that over here, right? This non-uniqueness, the non-uniqueness of representation. So in this situation, if you want to have this constraint here, where you have exactly n neurons, but the number of layers, I don't know to explain what a hidden layer is, but just it's the number of layers. So disregard hidden. We didn't have time to go into that distinction, but if we have this constraint with n neurons and at most L hidden layers, then we have this kind of issue where it's not really a combinatorics problem. You end up just having to sum over a combinatoric symbol, but the issue becomes that okay, if I try to represent if I'm talking about like okay, L is 3, so I have at most 3 layers, but I try to represent since I want at most 3 layers, I want to be able to talk about what it means to have 2 layers or 1 layer, right? If I try to do that by inserting zeros, considering or talk about configuration like this, like 0, 4, 0, 6, that means 0 in the first layer, 4 in the second, 0 in the third, and so on. In fact, this is the case where n equals 4, not 3, but you get the idea, right? So the problem is that this configuration is like a 4 in the first layer, 6 in the second layer, and that has this representation in terms of stars and bars. But if this is an equivalent way of doing the same thing, right?
And the gist of it is basically that you end up with multiple stars and bars representation mapping to the same neural network. So you can overcount if you do this.
So that's why this didn't come out to be such a nice combinatoric problem.
Yeah.
So,
like all the configurations lead to basically the same neural network.
Yeah.
It doesn't matter which layer you delete. You
Yeah.
have the same allocations of the remaining layers the same, so you've got like a whole bunch where you're just doubly counting.
Yeah, so you've got these 3 different sequences of stars and bars here, right, that lead to the same neural network structure.
Yeah.
Because of the zero.
Huh?
Because of the zero.
Yeah, exactly. Exactly.
Because if you try, thinking about, okay, I'm just going to delete a layer by not having any stars in that bin, right? Then there's multiple ways you can do that. So that makes that messes up again. You have to have a clear one-to-one correspondence between your network configurations and your sequences of stars and bars, right? If you don't have that, that's violated here, because I have multiple representations of the same architecture.
So
right?
I guess you could account for that by like subtracting would it be like 4 choose 2 or something like that?
It's a good question. I haven't really thought about it. Yeah, maybe you could account for this some way.
Yeah.
But
I did suggest that and you yelled at me, so stop.
Yeah, but you're not Brian. See?
Oh, okay, well, fair enough, I'm sorry.
I never yelled at you. Shut up.
Fuck you.
Shut up.
There you go. But yeah, but I'll let you take it out too, right? Because then it's like, well, you just want to subtract all the duplicates and keep one.
Because then you have like, basically you're choosing spots for the zeros then.
Yeah. It seems like there's some way, it feels like there's some way to do it, but I thought about it for a while. I don't know, I'm happy to think about it. If you want to think about it now?
I think about that.
Yeah, because I mean, if there's a way to subtract all those extra duplicates and just keep one, it makes for a nicer representation that easily maps onto everything we know about stars and bars, right?
When you say subtract, what do you mean?
Like how many ways
Just
that
a
you
number.
choose zeros?
Like a number,
Yeah.
how many?
Yeah.
Okay.
Yeah, and then if you subtract that from the initial, then you get rid of the duplicates.
Well, yeah, well, it seems like you do the same thing that we did for the formula for combinations. You just divide by the factor, by the number of, so basically
Yeah.
what you're doing here is, you say you're choosing places for the zeros, right? I was looking at it more like you're choosing a spot for the 4 among the first 3, I guess, slots, right? So it'd be what? 3,
Yeah.
3 choose 1, right? So you divide by 3 choose 1. It doesn't help you, I mean, yeah, I thought you meant initially like determining which, I don't know the word.
Yeah. But yeah, like how many
valid ones, but yeah.
Right.
How many ways can you
Straightforward
choose?
enough, yeah, yeah.
Otherwise, can you choose 2 0 layers out of a neural network, subtract that, add it, and then just add one because you want to choose one of them, and then maybe, but I'm still not there. But yeah, it would seem like,
What you guys think about it?
yeah. But I was saying, because you got like 04, 06, right, and you're looking at basically two layers, so in configuration, like that specific configuration, but then you have to like figure out all the other configurations, right?
Yeah.
But the idea is that, you know, hey, how many ways can we have, you know, 2 0 layers, 1 0 layer, and then you just add one each time just to retain that one unique, that one case. But again, you still have to sort of sum over all those different ways of getting it.
So that's probably a way to just aggregate all the time to a formula or something.
Maybe.
So,
Maybe. So yeah, I definitely see what you're saying. There's like, because these like 0406 is equivalent to 0046 and so on, right? So you could just collect them all into one set of things that are equivalent to each other. That's one approach. So that's what kind of like I think what you were suggesting, like with respect to the permutation. You take permutations, divide by the right factor. It's like you're dividing out. You're just that division is essentially you're collecting a bunch of things that are equivalent to each other, right? And dividing by that the number of those things.
Yeah, how to generalize that into a formula. I'm not
yeah,
sure.
that's where it gets fun.
I'm not sure how that can be applied here. I think that's a very good thought that you could try that. I'm not sure it's going to work 100%, but and then the idea of subtracting out, like computing the number of things that are extra things you have, and then just subtracting it out seems like something that could work. I'm not sure that ultimately you get a formula that's simpler than this, honestly, but.
I think it's going to be hairier.
Yeah.
I don't know. It's something to think about if you have time.
Yeah, because this formula like necessarily is overcounting, right? So
Yeah.
you're going to have to remove something from it. So yeah, I don't think you could get any simpler than that. And the way that the formula for permutations is simpler than the one for combinations because you're overcounting. I'm agreeing with you. Yeah, like I don't think whatever the general formula is, it's not going to be prettier than that. It's not going to be simpler than that.
Okay. Well, no, it's just a bit caught off by what you said that it's overcounting. But
For the 0 layers, because when you include the non-uniqueness of the 0 layers, it's not accounting for that. So that basically overcounts. Or you can say it gives you an upper bound on it, but of course you have.
Yeah.
okay. Yeah. So I mean, this formula is essentially just taking the previous result, by the way. It's taking this previous thing, right? And say, okay, well now we're just let L be I, and let I range from 1 to L.
All right, or say if you do allow for the 0 layers, then that of course is going to be overcounted.
If you allow for this, yeah.
Yeah, that's what it says. That when you allow for the 0 layers, that overcounts. So
Yeah, I got you. Okay. Cool. Yeah, and then we did this one, which, we won't go into, but yeah, this seems to me like the more realistic scenario, right? Where you have, maybe you have some sort of limit on computation, right? So you can only have so many neurons, right? Like there's some upper limit imposed on the neurons, right? So you have at most neurons, but for whatever reason, maybe your problem seems like it should have a certain number of layers exactly, right? So, okay, I'm fixing the number of layers that I'm gonna have because, problem considerations or something. But my computational limit is imposed, so I can only have I have an upper limit on the number of neurons, right, that I can use. So this, this is again, what you do is you sort of modify the rules and it comes out to be exactly n choose L in this case. Okay, so again, you have to come up with how to represent, the permissible architectures in terms of these stars and bars. And one of the innovations is just that you can have, like as in this example, you can have a bar on the left. And in fact, the convention is that the leftmost bar delineates all the neurons that you're going to throw out. So now you can consider, situations where you have different numbers of neurons by making the first bin the throw-out bin. So that's the convention that I've adopted to solve this problem. And so as such, you can have a bar on the far left because what that means is that you're not throwing out any neurons. So the throw-out bin is empty in this type of example. But if the bar is moved over here, then that means that any star to the left of it is representing a neuron that's thrown out, it's not used. Okay? So yeah, when you do it, it comes out to exactly n choose L. And then the final case where you say, okay, I want to have at most n neurons and at most L hidden layers. So you're considering all possibilities. Then you just have all I could think to do is just resort to summing again but now I'm just, again, what I'm doing is I'm changing the L into an I and then just summing from I up to, now L is an upper limit on the number of layers. Right? And that's it. Okay. So there are ways also to estimate this. If you're really super interested, you could look at Stirling's formula, give you something to make this into a more concrete formula. It's just an estimate. It's a good estimate. Stirling's formula for factorials, estimated factorials.
Questions? Yeah, when we iterate through it, and I remember this was a while back, something, I don't know if it's from decision theory or whatever, that said that if you're trying to make a decision, you had a huge number of choices. That one rule of thumb was you go through 30% of your choices, reject them all, then the first one that's better than any of the 30% you go with. So if at least you have an idea, and I think statistically it's supposed to perform good in the long run, so at least you know what sort of space is available to you. At least when you hit that 30%, assuming you can even afford to iterate that much, right? So you got to use something like this when you're trying to brute force it and use that as a rule of thumb for picking your ideal neural network, or at least a good enough one.
Yeah. So that sounds like some version of the Pareto principle, right?
It might be.
I don't know, maybe not.
Something I encountered years ago and I thought was kind of interesting, but I don't recall what it was called. I thought it came out of decision theory, but again, don't quote me on that. But it seems like an interesting application, at least knowing how far you had to go before you do it. But these numbers can get very large very fast. That's the thing.
Yeah. So that's the idea of these, why have these formulas? Why care about solving this problem? So, well, if you find that you really have to test all these architectures, then you at least want to know, how much that's going to cost, right? Before you get started.
Yeah.
So.
Or if you want to do testing over, say, a complex page, you want to get an idea of what are the possible states, and can you afford to test them all, or you want to go random sampling, and how much random sampling you want to do, right?
Right.
And at least so it's really kind of resource management.
Right.
I forget the name. He has a way for optimizing the neural network structure, but he just starts with one node, and and then he will incrementally add nodes to it, and then he'll add a layer, and then basically, and he just, I don't know, he has a procedural way of just adding one node at a time and creating, and one layer at a time with optimal structure.
I'm gonna check it out. Do you remember the guy's name?
And then you can do on YouTube.
Because designing optimal neural networks is an interesting problem. So there's some good heuristics I would definitely like to figure out on that. Because I was like one of the irritating parts was like, well, what's the architecture going to be, right?
Yeah, that's like when you start studying about neural networks, it's just like you can just like what? How many layers should you have? How many neurons do you need? Just all seems very arbitrary.
Yeah.
Right.
There's some rules of thumb, but again, you don't really know like how good they are. Yeah. Like your input layers, like okay, fine. Input layers, one for every input. Output layers, one for every classification, right? Because that's all a hidden layer is. You've got your inputs, which is one layer, your outputs, which is another. Everything in between is the hidden layer, right? So the idea is like, okay, your inputs and outputs are easy. It's everything in between, which is kind of a pain. And anything.
Yeah. The procedural formula is called a cascade.
What's it called? Do you mind like texting it to me or emailing me? Because I wouldn't mind doing some reading. Because I'd love to know what's out there.
The professor invented the method. He claims it's actually equivalent to a gradient boosting.
Equivalent to what?
Gradient.
But I can't really see. I can't really imagine. I can't visualize how it could be equivalent. But that's what he claims. I'll send you. It's nice because you don't have to do any of this.
Yeah. Because this is computation expensive.
You just use the algorithm and it will automatically create a good enough neural network.
Yeah. Yeah, no, there's definitely an algorithm that's been preferred to this because I mean, it's like, this is expensive.
Well, depending on what you do here. So all this does is just calculate the number of possibilities, given
Right.
strengths. So at that point,
If you're going to try to brute force your way to it, even,
don't do a brute force. Like I can tell you, like, well,
Right. But yeah, but I mean, if you're in a position where you don't really know what else to do, then at least it's good to know what you're in for, right?
Right. At the very least, you can do a random.
You can type it in, but just Google cascade correlation and deep learning. The guys,
How do you slow chickens?
cascade correlation and
Cascade correlation learning architecture.
it's better if you show the YouTube video. He gives some visualization. The YouTube video is really, really long, but you could just skip through it and just listen.
So this is just like
That's abstract. Yeah, can you send me the link or just text me the link or whatever?
Yeah.
And I could do some research and video watching at home.
This looks like super old.
Yeah.
It is all because there's another like link in Total's data science that says it's the forgotten method. So
This is not even like I can't even control F this PDF. That's how.
you don't have the PDF.
Well,
It is
it's like an old paper.
It is old. But he did a presentation on it recently in 2019.
It was like typed.
It's better if you just watch the YouTube video. He explains it more intuitively on it. If you Google YouTube.
It's citing papers from the 80s.
I mean, a lot of these concepts go back.
No, I'm not throwing shade. I'm just saying this is this is an old paper. That's all I'm saying.
I mean, all these but goodies, man.
The boosting part was so he adds each iteration he adds an extra neuron, and after he adds a neuron, the boosting part was he finds how well it performs, and then he removes the lower performing ones, and to figure out which run better. There's multiple dimensions, so you get a gradient of the correlation. it's hard, actually, I don't even know what I'm talking about.
Yeah.
But
It's not your flow.
he said,
Something like
he
that.
doesn't, he somehow is able to relate how well every time he adds a neuron
Yeah.
to some correlation matrix.
Okay. That's fine. I mean, if you
And he just in each iteration he removes the ones that have the least correlations
Okay.
somehow. I don't know how he relates the correlation to how well the neural configuration performs.
That's fine. I mean, main thing is he gave us a link, so that's something for further research. So no, I'm gonna at least know where to look up.
No, just watch the YouTube video.
Well, yeah, I'm watching the video first because I can sit around with a bag of chips and shove it down my throat while watching it.
And he has to and there's actually a GitHub repo with this code.
Okay.
No. There's an online repo. He posted his source code somewhere online. And I was able to get it to work. Actually. I had no clue what it was doing internally, but I was able to get it to compile.
Yeah, no, that's fine. I mean, the video is a good starting point because this is an interesting problem. So I appreciate it. Thank you.
I'm kind of thinking at some point to do neural networks, kind of like a deeper dive on neural networks in general. Is anyone up for that?
A deeper dive in deep neural networks.
Not.
The joke was there, okay? I mean, but is anyone interested in maybe going into that or?
Yeah.
Deep learning dive into neural networks.
Deep learning, deep dive into deep neural networks.
We're gonna learn deep learning deeply.
I'll figure out some way to cram a few extra, but okay, yeah, I'm very interested in that because there's a fair amount of stuff around that in mathematics and neural networks and just
Yeah, we can get into matrix, linear algebra. Neural networks are basically just a bunch of fancy multiplying matrices.
Yeah. if y'all okay with that.
I mean,
What you're interested
doing
in.
the predictive side, not the training side. Training side, you need calculus, but
Yeah.
yeah.
We can focus on a predictive side for now, and maybe calculus for the next one. Training sites, we definitely want to bite off more than we could chew. But yeah,
I kind of want to show what neural networks are doing from like a kind of an intuitive standpoint.
but
If
in
I
terms
can
of
manage
training
it.
or in terms of
Yeah, what they're internally doing training. Because there's this notion that they're a black box, right? But that's not entirely true. There are ways to kind of suss out what neural networks are doing.
Well, I mean, in terms of black boxes, though, is the complaint that they're a black box because it's not obvious analytically, what they're doing. I mean, you've got everything you need, but trying to actually get, for example, a linear regression. You can tell what it's doing by just analyzing the formula and what's important. Whereas with neural network, you've got everything, but making heads or tails of it is a whole other question, right? I think it's what they mean by black box.
Yeah.
That's why they got all the interpretable neural networks and the fun stuff in genetic programming and all that to try to estimate them in a more tractable way.
It's like a neural network to analyze a neural network.
But then how do you understand that neural network is going to analyze it?
Make a neural network.
Neural networks all the way down.
Like a simpler method, they just build a graph like you guys did before, and then you can drill into the graph to see exactly how the results were obtained.
They have that. They also have there's some work on doing interpretable neural networks.
Right.
And so what they're doing is they're trying to estimate what the neural network does, but you actually give it a limited basis of functions you could use, and so it produces an algorithm that simulates a neural network, maybe not as precisely, but close enough, but it's a lot simpler to understand. And there's a whole bunch of interesting stuff. They actually use genetic programming to try to do that. So, and there's even Python packages where they try to do that. It's pretty interesting. So they do have that, and that's actually, and I think I sent you some links a while back. I thought that was pretty interesting what they're trying to do with that. But yeah, it's interesting stuff just because you get into things like biases and people not being able to really know where it is, and it's well, yeah, you've got the neural network in front of you. It's I have 500 layers with a bunch of numbers. Good luck at analytically, figuring out, but yeah.
Right.
But yeah. So okay. So next time you said did you want to get into the training? If we're gonna do the
We can do
training.
it next time, but maybe we can talk
Yeah.
about that.
Because yeah, if we're gonna do training, then I think the whole session has to be on training. If we're gonna be doing prediction of linear algebra, probably should be on that, right? Just because it's a lot of material, it wouldn't be
You
just
can
one session.
just do the linear algebra bit.
Yeah, I'm fine with that for next time, yeah, and then if you want to do calculus on the training for the time after. If there's interest, we can check. So okay, like maybe doing a neural network prediction and linear algebra behind it and, okay?
Basically, how do neural networks make predictions?
Yeah, with guest star in linear algebra.
Yeah.
So-
Just matrices.
Okay, you all good with that? Good? Okay, cool, so we have our next job.
We have our marching
Cool,
orders.
yeah, yeah.
Okay.
Again, we're always open to feedback, so definitely let us know if there's something we should look into, because we definitely like having ideas. Keeps us from like, squabbling over what we want to present next.
Yeah.
Cool. I mean, I like to squabble, but still, not everyone does. Awesome. Then I think that covers it. So any questions in general, or? Okay, cool. So remember, if you scan a QR code, you'll have access to the LinkedIn group. I can let you in it, if you ask me, let in. And I'll have the link for this set up. If you're not in LinkedIn, you still need the link, please let me know. I'll provide it to you, I can email it to you, whatever. If you have any problems trying to get to this, just let me know. I'll make sure you can get to this, and then you have access to all the code, you can play around with it. Experiment with generators, get an idea of how they all work and why Python uses them, if there's a reason for it. And ask me any questions you want, or us any questions. Cool? Awesome. And yeah, then thank you for coming, and hang around.